neighborhood of philosophy of making a name for yourself by setting yourself out as an iconoclast. Also by referencing popular culture. So in a recent manuscript and in several talks, Gordon Belot has been arguing an iconoclastic line on isometry and physical possibility when it comes to space-time theories. He wants to argue that some isometric spacetimes can represent different possibilities, or what he takes to be equivalent to that. He's indifferent between the statements of these two and slides between them. Some isometries generate new physical possibilities. And in particular, he wants to argue this by saying that we have to take the practice of theoretical physicists seriously, in contrast to philosophical consensus. That these theses are supported by reading off the practice of theoretical physics. So, Jim mentioned that all pictures of philosophers of physics are taken in a certain room. This is no different. So what Gordon wants to argue, and this is his title of his manuscript, is that 50 million Elvis fans can't be wrong. What he's referring to here is he's referring to the fact that there is a large community of physicists who think about physical possibility, what he calls modal concepts, in a particular certain sort of way. And that in virtue of the fact that there's so many of them, and in the virtue of the fact that they make a more or less coherent community, they can't be wrong about that. Now, he, in appropriate parentheticals, says, well, maybe this is a little too strong, but the point is we need to really pay attention to practice of theoretical physics in a way that the philosophical consensus on the relationship between isometry and physical possibility has not. So, what I'd like to argue, and which is also a break from tradition in two senses. One, that this is not in that building. But I want to argue that they can be wrong if Elvis has left the building. What do I mean by that? Let me be a bit more precise. So my differences with Gordon is that I actually agree with him that some isometric spacetimes can represent different possibilities. But I disagree with him that this statement is equivalent to the statement that some isometries generate new physical possibilities. And I want to argue against the thesis that these, and the equivalence of them, is supported by the practice of theoretical physics, and that this is in contrast to philosophical consensus. So, who is Elvis? For Gordon, Elvis is a certain conceptual consensus on the relationship between isometry and physical possibility. What I mean that Elvis has left the building is that the conceptual connection between those two that Gordon perceives in the physics community was never really there in the first place. Right? 50 million Elvis fans are waiting for Elvis to play, but Elvis is not even in the building. Elvis isn't around. They're waiting for something that isn't there. And moreover, they're in the kind of position that if they knew that Elvis wasn't in the building, right, they would disperse. They wouldn't be waiting for him to play. What I mean by this is that the grounds on which I want to argue that Gordon is mistaken are grounds that the physics community themselves would accept. Right? So it's not philosophical consensus imposing new kinds of standards on the physics community, but rather thinking really hard about the standards that the physics community already aims to accept. So my positive theses are that the critique of the relation between isometry and physical equivalence that seems to be in contrast with the physicists that Gordon is talking about is not revisionary. This got caught up, but it's supposed to say that attention to the standards of applied mathematics clarifies this relation. and it clarifies it in the way that is entirely analogous to the way that attention to the standards of applied mathematics clarifies the whole argument. And this is what I take actually to be really important in that understanding. The representation relation is not one-to-one or many-to-one, but many-to-many. That will play a crucial role in understanding Gordon's examples. So first, I want to say a little bit more about methodology in philosophy of physics, because Gordon explicitly puts a lot of the weight on his argument on a certain methodological point about the role of philosophers of physics vis-a-vis physicists that I think is a little too quick. Then we'll talk about his example. His example involves isometry and physical equivalence in space-times that have a certain special property called asymptotic flatness. Then, in order to reinterpret that example and diagnose what I think is going wrong, I'm going to talk a little bit about flesh out more about what we mean when we talk about the representational capacities of a particular model. That's where this many-to-many relation is going to come in. And finally, I'll get back to the analysis of Belot's example and draw some conclusions from that. So here's Belot talking about his methodology. About some things, such as the fact that Elvis was peachy keen, his legions of fans could not be wrong, just because there were so many of them. Similarly, what similarly might makes right whenever a large group of people use a word or concept in a certain way. There's a large community of people, physicists, according to whose mode of concept shifts, that is, diffeomorphisms, and the push forwards on the metrical and other geometrical structure on the manifolds on which we're acting with the diffeomorphisms, generate new possibilities, large, that is, relative to the number of philosophers interested in these matters. So shiftless philosophers are engaged in a revisionary project of trying to construct new modal concepts to replace ones in common use. So I think that there's something wrong with that. And to do that, I want to construct a fictional character. Compare the fictional Jordan Benoit, writing, say, a bit before 1950. Here's Jordan. There's a large community of people, physicists, according to whose principles only measurements provide meaning to physical quantities. Large, that is, and relative to the number of philosophers interested in these matters. So realist philosophers are engaged in a revisionary project of trying to construct new principles to replace ones in common use. I think that if we really take Gordon's methodology seriously, we come to a rather disturbing conclusion about the whole history of the field. That philosophers' insistence on getting clear about the measurement problem was mistaken. And it was mistaken precisely because a huge number of physicists were agreed that the problem wasn't a problem, right? That it had already been solved. And that, therefore, philosophers engaging in the project of trying to interpret quantum mechanics were actually revisionary. They were trying to come up with a new set of concepts to understand the quantum world. So what's wrong with this? One of the things that I take what's wrong with this is that the philosophers engaged in the interpretive project of quantum mechanics were trying to engage with physicists on the very same grounds that physicists would accept. Now, I want to make clear that this historical case that I'm making actually has some support. So here's Matsuyama in the philosophy of quantum mechanics, right? Writing about the dominance of, in particular, Heisenberg's thinking on quantum mechanics, right? So it would be difficult to find a textbook of the period which denied that the numerical value of a physical quantity has no meaning whatsoever until an observation has been performed. Now, I think, to say it one more time, I think that the thing that's gone wrong with the methodology that Gordon is putting forward is that he's assuming that the kinds of concerns that philosophers are engaged with use different ideas, standards, and methods than physicists are. But I think that in some cases, that's not the case. And in this case, I don't think that's the case either. I'd like to take a tack here from the kind of methodology that Maddie advocates in her second philosophy. She's mostly interested in applying this methodological idea to interpreting debates in foundations of set theory but I think that it's a general set of methodological principles that is helpful in our project as philosophers of physics. In other words, it's true that it would be fruitless to hold physicists to methods, standards, or ideas that are not relevant to their work, right? It's not relevant to the project that they take themselves to be engaged in. But philosophers can and should engage in critique using methods, standards, and ideas already accepted by the physics community. And this includes the ideas, methods, and standards of applied mathematics. Even though physics can't always achieve the complete rigor of mathematics, it at least aspires to it. When it can be achieved, it's a worthy goal. So the critique, I think, to be made of Gordon runs along those lines. It's not a revisionary project, but it's a project using the methods and standards that the community already accepts. So here's the standard story, right? This is a diffeomorphism, right, is going to be a smooth convertible map between manifolds, and we say that if we have two Lorentzian manifolds, we can push forward the metric along the diffeomorphism to obtain a new one on the new manifold, and we can compare it with G prime. So if they're equal, they're said to be isometric. Okay, so what is Gordon's concern? Gordon's concern has to do with spacetimes that have an extra property to them, an extra property called asymptotic flatness. I have to be very careful here. There are a great many number of different notions of asymptotic flatness. For those of you who have used the concept, you're probably most used to the concept as it's used in the method of Penrose, where one constructs a boundary of a conformally equivalent space-time and talks about some of the algebraic properties of that boundary under certain sorts of symmetry considerations. Gordon is actually interested in a slightly different sort of notion of asymptotic flatness. He's interested in space-times that can be equipped with an auxiliary Minkowski metric, such that the original space-time metric and the Minkowski metric approximate one another arbitrarily well as space-like infinity is approached. Now, in order to make this idea precise, of course, one has to perform a preferred foliation of the space-time so that one can compare the appropriate space-like slices. But a lot of these details are not so important. Gordon doesn't go into them so much either, and so I'll try to meet him on that level of detail. But the basic idea is that imagine you have some star, right? You have some star which, in virtue of its matter, energy, content, corresponds with a curvature of space-time. And there's a sense in which we want to say that in a particular spatial slice, we can perform a certain integral and talk about the mass contained in this solution. Right? So the bonding mass, the ADM mass, these are all quantities that require this sort of integral, but they require reference to a particular sort of structure. So the idea here is that we take a Minkowski-like metric, right, and we put it on top, and we can use that to perform certain types of calculations. Because the real metric, the physical metric, approximates the Minkowski one, we can use some of the special symmetry properties of the Minkowski one to perform certain calculations and talk about certain conserved quantities as well. So in this particular example, one thing that you can talk about is you can talk about the deflection angle of a beam of light incident around a star. In order to be able to do that, you need to compare the trajectory of the light ray had it been in Minkowski spacetime versus in the curved spacetime. So Belot wants to make the following argument. He wants to say we need to distinguish between what he calls two sectors of general relativity. One sector is cosmological, and the other sector is asymptotically flat. The cosmological sector represents possible whole universes, whole histories of the universe, whereas the asymptotically flat sector only represents gravitationally isolated subsystems in the universe. Now, the structure of a general cosmological model is a Lorentzian manifold, but the structure of an isolated subsystem is a Lorentzian manifold plus this auxiliary Minkowski metric. Right? That auxiliary Minkowski metric gives it the asymptotic structure that we need. And he wants to assert the following. What are the isomorphisms? The isomorphisms that generate no new possibilities, that are physical equivalences, what he likes to call gauge equivalences, although I'm not going to use that terminology. In the case of the cosmological models, it's everything. But when the space-time is equipped with asymptotically flat structures, it's only the asymptotically trivial diffeomorphisms, which are the ones which produce no new possibilities. What it means for it to be asymptotically trivial is that if you look at one of the spatial slices, as one goes to infinity, the action of the diffeomorphism closer and closer and closer approximates the identity. So in this case, he thinks that the relevant isomorphisms, which are just isometries, don't generate new possibilities. But in the case of asymptotically flat spacetimes, any isometry which is not asymptotically trivial generates a new possibility. Why does he say this? Well, he has a bunch of arguments. And a lot of them, like I mentioned before, have to do with looking at the way that this seems to be used indispensably in physical practice. I think the most illuminating example that he gives has to do with conserved quantities. So consider a time-like Pulling vector field, whose integral curves form a geodesic congruence with respect to this auxiliary Minkowski metric. So these are just parallel, so these congruences are just parallel world lines, right? They're fully in this sort of way. Form a congruence of the space-time. So these in turn generate one parameter family of diffeomorphisms, and we can label them by T. So then you can compare the space-time with the asymptotic structure, right, with the space-time that we get when we hit everything with the diffeomorphism. So we hit the manifold with the diffeomorphism, and we're going to push forward all of the structure on it. Now, in this case, right, because it's a time translation, the Minkowski auxiliary metric is invariant under that. So what we can do is then we can compare this one with this one. Now, here's Belot's argument. If these are considered as physically equivalent, right, as would be required if we consider all isometries, right, to generate physically equivalent possibilities, then a seeming time translation of the space-time produces the same effect as the identity, right? If we think that this is physically equivalent to this, then the result of this is the same as implying identity. So we reach a puzzle. It seems that acting on a space-time with the identity diffeomorphism gives us the same result as acting on it as with a time translation. Woe then to conserved quantities. That's the argument. So the important thing here is that this particular sort of diffeomorphism is not asymptotically trivial, right? It shifts spatial slices from one to another. Okay, something's gone wrong. What's gone wrong? So my diagnosis of this is that a problem and an implicit assumption of Borden's argument is the assumption of representational uniqueness. The problem, in other words, arises for isometry equaling physical equivalence is only a problem when it's married with representational uniqueness, which is the thesis that every mathematical model, in this case, every space-time, represents a unique set of phenomena, unique physical world, or a unique state of affairs. And then the gauge equivalence, in his terminology, of diffeomorphisms, in physics and in space-time theory more specifically, is supposed to denote the many-to-one nature of representations. But this sort of many-to-one nature of representation assumes this representational uniqueness. If one has many different space-times which are isometric to one another, they all represent, and one sees this language, the, right, definite article, the same physical possibility. That's the sense in which it's many-to-one. But I think we actually have a lot of evidence the representation is in general not a relation, general relation, a proper relation, not a function. So some think, right, that the proper formulation of a mathematical theory with regards to representation should be like this, one-to-one. And that the problem with theories that have gauge in them is that they're many-to-one, and that we need to quotient them by the equivalence relation of this representation relation to collapse this sort of situation into that situation. I want to argue that actually the generic situation we find in ourselves in is not just one-to-many, not just that one space-time can represent many different distinct physical possibilities, but that it's many-to-many. Many different space-times can represent many different physical possibilities that sometimes overlap with one another. So I'm going to give you three kinds of examples of this. One, multiple types of system. Another, multiple physical scales. And three, when we add a little bit of extra structure, the relation of different models to one another. So I think the first example is something that you're all familiar with. It might not be so convincing, but I think it's worth saying anyway. Mathematical models don't know springs from current. Now, you would never confuse a spring with an electrical current, right? But the mathematical model, the solution to a differential equation in an LC circuit and a simple harmonic oscillator is the same. But what the different terms refer to in this particular case are different. Okay, so this much can be agreed on, but the natural protest, of course, is that, well, usually we delineate, right, the class of physical situations. And these are so disjoint from one another that we usually focus attention just to blocks connected to springs or simple electrical circuits. But there's another type, which is multiple physical scales that we don't find. So, to put it in a word, mathematical models don't know meters from kilograms. So, let me say what I mean by that. So, here is, in standard coordinates, the exterior Schwarzschild metric, where RS here is the Schwarzschild radius. Now, in this model, right, one usually says that one picks units so that the relevant constants, right, the gravitational constant G, the speed of light c, have the numerical, take on the numerical value of 1. Now, we do think that there are different Schwarzschild spacetimes, right? That there are some that can correspond to very, very small black holes. There are some that correspond to very, very large black holes. Now, but in the mathematical model, the Schwarzschild radius is given by a number. It's something that's external to the model about what type of physical unit that quantity represents. So this model with a Schwarzschild radius of 1 could be a black hole with a 1 meter Schwarzschild radius. It could be a black hole with a 1 kilometer Schwarzschild radius, 1 megaparsec radius. All of these can be equally well represented by this particular metric. Now the issue is that if we were engaged in a project of quotienting out, right, taking as physically equivalent, right, all of the models that are isometric to one another, obviously this is isometric to itself, but we would never say that a Schwarzschild black hole with a 1 meter Schwarzschild radius is physically equivalent to a Schwarzschild black hole with a 30 million parsec radius. So one of the things, in other words, that the mathematical models, not just a relativity theory, but in general, need to do is they need to say something about how the numerical quantities are referring to physical magnitudes. But that's something which is not determined by the mathematics themselves. Now, as a kind of bonus, right, we can also have a kind of opposite situation where we have non-isometric models that can represent the same class of spacetimes. So I say like homothetic. So homothetic spacetimes are ones whose metrics differ only by a constant factor. So here's the Minkowski metric. Now we can consider another metric, eta prime, which is just eta times a multiplicative constant. it's extremely common in the physics literature to say, look, these are really the same space-time, or that these two metrics really have the same representational capacities. They just differ by a change of units. And indeed they do. But strictly speaking, with regard to the mathematics, they're not isometric to one another. And this is the sense in which we have a many-to-many relation. I think that the really important point, though, for Belot's example computer went to sleep. Oh, the power. Okay, that's a problem.
Let's jokes now.
So, well, I can. Does anyone have a deck of cards? But it's serious because. Right. We're restarting now. We have to wait for it to restart first. So there's another aspect to it, though, right? And the other aspect to it is that by describing, I do want to do that. Because different models can represent now many different physical situations. By connecting them in a family, right? By providing a standard of identity by which we want to compare how they're doing their representational work, we can have a situation where we have a whole family, a whole class of isometric spacetimes that represent a changing physical situation. So fix a standard of identity, right? Suppose that it's just the identity map on the manifold. Now pick a collection of models, and this might be the image under some symmetry. I had the example of a timeline killing vector field before. So now we can use that symmetry to generate a class of models. How are we going to compare all of those models to one another? Well, we have to use the standard of identity that we fixed. Each model, in this case, may be isomorphic to each other, in this case, isometric to one another, but the collection may not be isomorphic to the constant collection. The idea is this. So imagine that each card in this deck represents a space-time, right? And each of them can represent the same space-time. These cards are identical to one another for all the purposes that one wants to use cards to represent space-times. Now, we can consider a parameterized family, right, where each element is isomorphic to each other, but where we have this twist going on, right, where we've identified different points of the card with different points. Now, the fact that each card can represent the same situation as each other card doesn't necessarily mean that the changing family represents no change at all. It does. And this is essentially, I think, what the mistake that Belot is erroneously attributing to the proponent of isomorphism and physical equivalence is doing. So recall his example. The position against which he argues, one uses different standards of identity to compare models. So the standard of identity given by psi t is used to compare with this metric. And the one psi t prime is used to compare with this one. But this is the same problem, right, that we had in Jim's analysis of the whole argument. One has to pick a fixed standard and not compare different things, different objects in the structure that one is examining using different standards of identity. Now, one of the nice things is that if we had picked a different standard to begin with, not the identity map on the manifold, but some other diffeomorphism, we would still arrive at the same conclusions. And if indeed we hit all of the spacetimes in this one parameter family with the same diffeomorphism, right, then all of the conclusions that we want to draw remain invariant under that. Now, Belot's conclusion is that if we want to represent things like time translations, right, and the nice associated conserved quantities, we have to conclude that models that are related by one of these time translations are different possibilities. But we don't have to, or that these time translations generate new possibilities, rather. But once we drop the assumption of representational uniqueness, this conclusion no longer follows. Each of the particular models in the family has the same representational capacities to represent the same situation. But once we introduce relations between these, the relations between them need to be preserved if we want to act on the whole family by a diffeomorphism. So the question still arises, why do practitioners seem to limit attention to asymptotically trivial isometries in particular situations, right? The communities that Gordon is pointing at. My diagnosis is that if you use general diffeomorphisms, you'd have to compare this model with this model. And that's just really complicated, right? You could have picked one which is going to give us the same calculation, but which acts in a nice way on eta. So the main reason physicists restrict attention to these asymptotically trivial diffeomorphisms is out of practical calculational convenience, out of any metaphysical commitment. Thank you. Thank you very much.